So now let's try to understand the convolution operation. I will give you like some more insights. What exactly is happening when we are performing this operation? Of course, we have seen filtering, like how it works and what this filtering actually means. So let's say we have a function ft, and you can see it's a simple step function, or you can say like a unit function. And from negative infinity, it's at 0. And as you come to this point, it directly jumps to 1 and stays there, and then comes down and again remains 0 as we go to plus infinity. So that's a simple function. Let's say we have a kernel, which is like almost have like similar kind of structure. And again, this kernel is like, if you go negative infinity, it's 0, goes to 1, comes to 0, and stays there. Okay, so in this case, this is the function, this is the kernel, and of course these are like just one-dimensional functions and kernels. But whatever we are trying to discuss here, you can easily generalize that to two-dimensional or three-dimensional or any high-dimensional space. Now, if we convolve these two functions, treating this as kernel and this as function, now what exactly is happening? You know that when you convolve, you actually you flip your kernel, right? In this case, if you flip, it doesn't matter because it's kind of symmetric. It's just like your plus infinity will go to negative infinity, and negative infinity will go to plus infinity. Okay, so that's one thing. Then what you do is you try to apply this kernel at all the possible locations for this function f. And those locations will start from negative infinity. Of course, I'm not showing negative infinity here. We are starting from -2. Of course, you can extend this to negative infinity. And on the positive side as well, you can go to plus infinity. So you start from this point, you take your kernel, and then you find the correlation. All right. So what you see, this kernel is actually not matching with the function at this location. Okay, so the response will be 0, because you know that it's just element-wise multiplication. In this case, it's just 1D function, and we just have two values, either 1 or 0. And at this location, if you put the if you apply the kernel gt has value of 1, but ft, the function, has value of 0. If we take element-wise multiplication, that's going to give you 0. All right, so it's 0. Now what you will do is you will stride your kernel towards the right. Okay, and then you will keep computing that convolution value. So you keep moving towards right, and you can see like still it's 0, it's 0, it's 0. But as soon as you reach like this location, you're seeing like some kind of overlap between the kernel and the function. Because what's happening, if you look carefully, like this red region here, at this point, it's starting to overlap, and which is indicated by this yellow color here, right? So the area of this yellow color actually shows how much overlap you have between function f and kernel t at this particular time step. Okay, so then you will see as you keep going towards right, the overlap is actually increasing. And at the center over here, they will perfectly match with each other. And you see, you will get like a highest response. Okay. So this black plot over here, this is actually showing you the result of convolving kernel G with function T. Okay, so you can see like from the left, it's 0, it's increasing. At this point, there's a perfect match. Then again, it goes down to 0. Okay, so that's the standard convolution operation between two functions in a continuous space, you can say. I mean, of course, this is not like continuous, but still it's better than discrete. Okay, because we're trying to like apply at each possible location. So if you think about this, what's happening when you are trying to convolve a function in a kernel, of course, output is like some kind of response. And if the structure of the kernel matches with the structure of the function, you will get a very high response. Okay, so that's the key. We have like discussed this several times, and it will keep coming. And that's exactly what we're looking for. If you can match the pattern, you will get high response. If you don't match the pattern, you will get a low response. Okay, so that's the whole purpose of performing this convolution operation. And this is like the continuous equation, which we have seen earlier as well. Okay. So this is a one-dimensional, but in convolutional neural networks, usually we use 2D kernels, or you can say like 2D convolutions. So you can just extend these 1D functions to two-dimensional functions. In that case, instead of like looking at patterns which are one-dimensional, you will look at two-dimensional patterns. But the intuition remains the same. You're just trying to do pattern matching.